Hey guys, welcome back. I'm going to be going over chapter 9. We're going to be learning about the hydrosphere. So remember back in the beginning of the semester, we kind of divided the planet up into different spheres: biosphere, atmosphere, lithosphere, hydrosphere, and then the cryosphere. So last week, chapter 3, we started talking about the atmosphere. So now we're getting into hydrosphere. The next few chapters we'll be looking at lithosphere. And we talked a little bit about biosphere in chapter 8, but that's more chapter 10. All right, so let's get started. We're going to be looking at the hydrosphere, and of course, we're also going to be covering the cryosphere because they are not one and the same, but they're related. So before we get to everything, let's look at the hydrologic cycle, the water cycle. And I did talk about this a little bit before. I did talk about it in chapter 5, but it's important to bring it up, right? Because we're looking at the way water moves from the atmosphere to the lithosphere, right? And so we're going to be looking at water in this chapter. And so when we talk about water, it's important to divide and think about water in either freshwater form or in saltwater form or saline form, right? So those are those two different types of water. When we start talking about water as a resource, people will say like, hey, there's so much water in the ocean. Yes, there is, but that is not fresh water. And what we as humans rely on and what we need as a resource is fresh water. So we have water, which is stored in oceans, lakes, and streams. And then we have frozen water, right? 3/4 of all fresh water is frozen. And I'm going to show you a little chart on the next slide, which is really going to show you how much fresh water is really available to us as humans, because that's what's important. Okay, most of our water that is fresh water is frozen, and pretty soon that will be melted. Okay, so when we talk about water, it is a closed and circular system. So let's look at this. This is what I wanted to come to. Most of our water, about 98% of our water, is in the ocean. That's the major reservoir, right? It's in our ocean. Our planet is known as the blue planet. Most of our water is in our oceans, about 97.2%. Now, 2.8% is that fresh water, what we use for agriculture, for drinking, for agriculture and drinking, right? All those things that we need. 2.8%, that's not very much. And of that 2.8%, of this small percentage, 2.15% is frozen, okay? And about 0.6% is underground. And just this sliver here is what is available to us in lakes, moisture, atmosphere, okay? And so we do use a lot of groundwater, so I don't want you to think that the only water that we use is coming from this small sliver. We get a lot of our water from groundwater, and we'll talk about that in this chapter. So I just think that this chart here really shows visually how much of a important resource water is, and we're not using it sustainably, right? Some places get more rainfall than others, right? So some places are going to have more water per capita, right? And it's not going to be equal all around the world, right? Okay. Here's another chart, and the percentages are a little bit off by 0.1%, but almost the same, okay? And again, here is our hydrologic cycle. We have precipitation, evaporation first, right, and transpiration off of those lakes, oceans, and soil and plants. Then you have condensation. Then you have precipitation and runoff. I want you to pay attention to that subsurface flow, okay? So there are certain areas, different types of soils that are going to allow for more water percolation, so more water to go down deep and fill up these geological formations, which are aquifers. And so we'll talk about that in a little bit, but that's also really important to think about, okay? And how we use that groundwater, how we pump out that groundwater, and if we're doing it sustainably or not, because we definitely can overuse those aquifers and take out too much water too quickly that it doesn't give it enough time to recharge. Okay, so we have movement on and beneath the Earth's surface when water comes down as precipitation. You have surface water, right? And then you have groundwater. Surface water is going to be found on Earth's surface, obviously in streams and rivers, lakes, ponds, reservoirs, wetlands, and then groundwater, just what I was talking about. So this is just a little bit more detail of the past slide that I was kind of explaining a little bit. Groundwater refers to underground water in the subsurface zone where the pore spaces are completely filled with water. Underground water reappears at springs at surface via springs, and these are called artesian wells. So in this picture here, you have a really good, in this slide here, you have a really good picture of these artesian wells. They are places either naturally or pumped out. So an aquifer really is like these rock formations underground. Water comes down and it comes down and it percolates underground and it hits like this layer, right? We call this layer like an impermeable layer. It's going to be certain types of rock or clay. So different types of soils or rocks or sands are either going to soak up water and hold it, and some are going to act like a barrier, and so that water will fill up. And then all these little rocks here, and then all the water fills up and it comes to the top, and we call that the water table. So all this here would be an aquifer. So if it's like confined or unconfined, it's either a confined aquifer or an unconfined aquifer. And sometimes the water table will go up into a lake or around a lake or stream, right? So you can pump out that water, and it's good, clean, filtered water. It's naturally filtered. Wells or springs. That is why Artesia is named Artesia, because it was known for a lot of artesian springs, and that artesian aquifer that is found there. So Artesia, Bellflower, Compton, all those areas were once really, really good areas for farming and agriculture. So there is a Compton Creek that's located in that area. So all those names are like Artesia is because of those artesian wells within that area. The earth contains underground formations that collect and store water, which are called aquifers. Water percolates and seeps underground through cracks and spaces and gravel and sand. And some rocks are more porous. That's what we'll call it. I took a whole semester in groundwater, and I wish I paid more attention, but it actually was one of the most, it wasn't the most boring. It was an interesting class. But different rocks are porous in different ways. So some will hold more water than others, right? So it just really depends. So, you know, you can refill these aquifers. I know for Whittier, California, we get some of our drinking water. Some of it comes from a Whittier aquifer. Some of it comes from reservoirs. So it just really depends. And then you fill up those aquifers, because if you pump out that water from that underground area too quickly, what will happen is the land starts to subside or starts to sink. So you have to be careful too. And you can't over pump something, because it's not going to fill up as quickly as our demands most of the time. And so right now there's not really a lot of law for groundwater law. There's not a lot of regulations. So if you're like a really prominent farm, or you have like, you know, like more money versus your neighbor that is a small farmer, for instance, if you have the funds to use and take out a lot of groundwater, you could be taking out from underneath your neighbor's home or farm, and there's not really a lot of law for that. So that's also really dangerous. And so water law is a good field to get into if you're interested in this. So here is just another picture. You would take out that water through an artesian well from the aquifer. I'm not going to get too technical on this, but I do want you guys to understand that we get a lot of water from underground, okay? Aquifer depletion is kind of what I was talking about. It's like this overuse or excess removal of groundwater. It lowers the water table and you can completely empty aquifers. And especially here in California, the reason we have so much agriculture, and agriculture is really the main driver of our economy, is because of our sun, right? Is because we have great sunlight all year long. The only thing is that we don't have water. Water is a huge issue. And so we find that a lot of places are really emptying their aquifers and the land starts to subside or sink. And you can completely eliminate these aquifers as a result of feeding or using the water for agriculture. So look at this picture here. This is San Joaquin Valley. The land used to be up here in 1925 and 1977. This is what that picture was taken. This is just an example of what happens. It looks dramatic, but that is exactly what can happen because that water, it fills up those spaces and then once you take it out, it starts to subside. Okay, so I'll have a video to watch with this and maybe a discussion. All right, so let's look at our oceans. Where did our oceans come from? Do we know? Okay, the rain, but where did the rain first come from? So some people think it was like we got some of our water from this frozen meteorite that hit the earth, like this huge ice ball that hit the earth. And then some of our water came from when the earth was being formed, those first few volcanoes let out steam, and that kind of gave us our first rainstorm. So a lot of our knowledge of the ocean has been growing, and it's pretty recent because only until 60 years ago did we really have the sophisticated equipment to catalog and measure details of our marine environment. And 60 years sounds like a long time, but geologically it's really not, and scientifically it's just up and coming and new. There's so many things that we are learning every year from the ocean that we are discovering. I always think that we should invest more money into discovering more about our ocean and what lies beneath the surface of the earth versus going to like Mars or things like that, which is still cool, right? But we should invest a little bit more on understanding really what our oceans are like and what's in the center of the earth, because this is all theory. I mean, we don't really know what's in the center of the earth, and we'll get to that in chapter 14. So a large part of our ocean life is still unknown to science, which is really cool, right? We're always discovering something new. So a large part of our oceanic life is still unknown. How many oceans do we have? Well, some of you will say, okay, we have 4, we have 7, blah, 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 right? Yes, you're correct, but technically we have one interconnected ocean. It is a world ocean, right? Our oceans don't stop from the Pacific to the Atlantic, blah, or to the Arctic, Indian, whatever, right? So 3/4 of Earth's surface is covered with water. So just to keep things simple and to organize things, we have named oceans different names, right? We have the Pacific, Atlantic, the Arctic, the Indian Ocean, right? The North Pacific Ocean. And which ocean is on the coast of California, guys? Yes, the Pacific Ocean, and the largest ocean is the Pacific Ocean, okay? Please keep that in mind. That will be on your exam. So here's just some pictures of that. And then some smaller oceans like the South China Sea, the Yellow Sea, the East China Sea. You have the Mediterranean Sea, the North Sea, Baltic Sea. When I was growing up, it was the Antarctic Ocean. It's not called that anymore. Some maps have it labeled as the Southern Ocean, but it's really mainly the Atlantic, Pacific, and Arctic Ocean. movement of ocean water. So how do these ocean waters move? So you have 3 different ways: tides, currents, and waves. Really, waves are just any disturbance on top of the ocean, wind, a boat, a swimmer, anything is going to cause those waves. Disturbances of ocean floor can also cause significant movements in water, and we'll look at how some underwater earthquakes will cause tsunamis, and that's more of chapter 14 because those are internal processes. So let's look at tides. These are vertical motions of water. There's 2 different types. You have lunar and you have solar tides. And there is a gravitational attraction between the moon and the earth. There's also a gravitational attraction between the earth and the sun. Your lunar tides are going to be stronger than your solar tides. You can think of kind of like the earth surrounded by the ocean, like this ball of water, and the moon, I mean, obviously the earth is much larger, but there's still this attraction there. And the moon kind of wants to pull on the earth like a magnet, but it kind of, the ocean bulges to where the moon is. And I have a really cool animation for that. So here's the earth, here's the moon, and then you have the ocean surrounding it, and then it kind of like bulges like it's pulling towards the moon. And that's a very dramatic explanation there, dramatic picture. This is the earth, okay. But that's kind of what's happening in these lunar tides. Now, ocean currents. Ocean currents are caused by wind flow. Now, we know that there are places on Earth latitudinally where you have this either high pressure or low pressure, right? And then you have those trade winds. So on those westerlies, those are all going to affect the ocean, and they're going to cause these currents. Some are permanent currents too. Let's look at some currents or some, movements of water that unfortunately cause most of our trash in the ocean to kind of remain in one specific area. So under those subtropical highs, remember those, at what degree are they? Like 30 degrees north and south, right? Remember that? So what were highs? What does that mean? High pressure there. Remember, low pressure is that uplift, right? So that's kind of like at the equator where the ITCZ is. And so high pressure is kind of like this descending air, right? You guys remember that? So you have those permanent highs at about 30 degrees north and south. And those are these descending winds. So you have air coming down and coming down, right? And so this kind of like puts pressure on the water, on the ocean. So you kind of have like this toilet bowl sinking effect kind of. So any trash that is in the ocean, and I'm hoping none of us really like go to the ocean, like throw trash, right? But eventually if our trash doesn't make it to a landfill, it goes into the ocean. And unfortunately, most of our trash, all of our trash is like non-natural, right? Most of it is plastic, and every piece of plastic that has ever been created is still on the earth today. So it doesn't just disappear, right? It's kind of like plastic was the best invention, but it's also one of like the worst things, right? It's in everything. It's in our clothes, it's in our phones, it's in our receipts, it's in our household items. I mean, it is so pervasive in our life. So anything that is in the ocean is going to make its way to these, either the western, we call it garbage patch, and it's really just under these high pressure belts, or the eastern garbage patch. This is that Great Pacific Garbage Patch. So I wonder if any of you have heard of it, and if you have, there's like a lot of myths. Oh, it's this island the size of Texas, and it's just so much ocean. It's just this island of trash that floats along. That's not really what it's like. This picture here is just for attention, and it's not the Great Pacific Garbage Patch. This is actually a very polluted river in India. But the Great Pacific Garbage Patch is actually more dangerous than this, because a lot of our plastic that ends up in the ocean takes some time to get to where, just because it doesn't go anywhere else, to this Great Pacific Garbage Patch. And most of our trash is plastic. Now, plastics, when they're left in the sun, they have like this reaction with UV radiation, and the polymers like turn really, really tough, and they break down, they get really brittle, and they turn in, like, they break into shards. I don't know if you guys have ever seen maybe an old dashboard in your car, and it like crumbles when it's exposed to the sun for years and years and years. Think of that. Think of all the plastic just like crumbling. It turns into these microplastics. Now, these microplastics are extremely dangerous for the environment. So here is that zone of our high pressure, about 30 degrees, right? And so this is where you have all these currents, ocean currents, and all of our trash kind of ends up here, and it floats around here. And we call it the Great Pacific Garbage Patch. And right in the middle is this island called Midway Island. And almost once a month, they have tons and tons of litter that they have to take off of this island, because they're just like in the sweet spot to where all this trash floats. So this is Midway Island. Unfortunately, birds are not the smartest animal in the animal kingdom, and they end up eating a lot of things that they find, and these birds die because of the things that they ingest, and it's all our trash that ends up in this ocean. So if it's not in the ocean around this island, it's on this island. So what are microplastics? Microplastics look like this. Remember, our water bottles break down into tiny, tiny pieces. Toothbrushes, gasoline, you name it, it's there. It turns into these tiny pieces. And that's extremely dangerous, because now these microplastics have been found in plankton. So what does that mean? That means that the very building block of our ocean's food web is contaminated with plastics, and we do our best, right, to eat clean, eat organic, not eat, MSG or hydrogenated fats, and we do our best to eat really, really well, but there's traces of plastic in our sea salt. That is how pervasive plastic is in our life. So if it ends up in plankton, it's going to end up in the sushi that we eat. It ends up in our food, and it's really damaging our ecosystem, our marine life, right? Another little point I wanted to make, yes, reduce your use of plastic, but there's also things that we're doing that we might not be aware of. So these little exfoliants that we buy at the store, they have these microbeads. Now, these microbeads are plastic beads that supposedly you scrub your face with. They go down our drain, and our water systems are not equipped enough to catch them, so they go straight into the ocean. And they're kind of like these super sponges, and they pick up everything toxic on the way from our sink to the ocean, or our drain to the ocean. So if you can, don't buy these anymore. Buy an exfoliant that is all natural, and you'll know it's all natural because it'll say you can only scrub your face with it twice a week, 3 times a week, every other day. These are made up out of plastic, and who really wants to be rubbing their face with plastic, right? Again, it is these corporations that have found a way to market things to us, because there's also a market for it, right? So that's just something to keep in mind. Do your part, right? Use less plastic, be more aware of what you are buying, and be a conscious consumer. How long till it's gone? Some things do biodegrade. Here are just some different facts, like a plastic grocery bag, 20 years. Styrofoam cup. Styrofoam is like the worst thing you can do. It releases a lot of toxins to make them, and they take forever to break down. So if you're going to use plates, disposable plates, use paper plates. Paper plates will break down. Aluminum can, 200 years. All this stuff, different things, right? And fishing line, you'd be surprised how much fishing line is in the ocean, and a lot of our marine life is being caught in these things. Okay, so those were currents, and now let's talk about another type of ocean movement. This is deep ocean circulation. So you have the way the ocean moves on top, right? Surface movement, and this is deep ocean movement. So we have differences in temperature and salinity, and that's going to cause different tides deep under the ocean, in the ocean. So you have differences in water density from salinity and temperature. Some places in the ocean is saltier than other places. Some places is colder than other places. So when you have cold, salty water, that's going to be heavier and it's going to sink. And so we call this movement of differences in salinity and temperature thermohaline circulation. So you have shallow warm currents, those are going to be more on top, and these cold deep water currents. So they're going to start in the North Atlantic Ocean, and you have water up there that a lot of it freezes, and so it leaves behind a lot of salt, and it's colder up there, and then that starts to sink and it comes all the way down. And then also, if you've ever seen Finding Nemo, and that stoner turtle, he's like, the East Australian current, and that's a real thing. It's like the East Australian current, and they're riding the wave. I don't know if it really looks like that, but it is a thing. So these currents are deeper, and we call this deep ocean circulation. This is a system of deep ocean circulation that happens because of temperature differences in water and salinity differences. Ocean water will become denser and will sink. If it's saltier, it also sinks a lot more. It happens mostly in high latitude ocean areas where the water is cold and salinity increases when ice begins to form. Sea salt is not taken up when water is frozen. Thermohaline circulation. This is a circulation of deep ocean water occurring. I just repeated myself. All this leads to the deep global conveyor belt. We call this the conveyor belt. It's kind of like moving around our ocean. It's mixing around our ocean. It begins in the North Atlantic. Cold, dense water sinks and slowly flows deep below the surface to the south, where it eventually joins eastward, moving deep, cold, high salinity water circulating around Antarctica. The global conveyor belt does not have an immediate effect on weather and climate as the subtropical gyres and other surface currents do. They don't have an immediate effect, but this circulation plays a role in energy transfer around the globe. Research suggests that a connection exists between ocean conveyor belt circulation and global climate. So it's not going to affect our weather, day-to-day patterns, current patterns, but it does have a connection between global climate. Remember, climate is over time, right? Weather is our day-to-day, okay? So I want you guys to remember that. It starts in the North Atlantic. This is everything I read from my notes here on the slide. Okay, so good, we're moving along pretty quickly. The cryosphere, this is another important part of the hydrosphere. This is just the part of the hydrosphere that is frozen. And it's either divided between ice on land or ice on water, floating ice, okay? Remember, the ice on land is going to be much larger than floating ice. So we have these different types of ice structures, ice formations, ice things, right? You have an ice pack, ice shelf, ice sheet, ice floe, iceberg. Pause it here, write these down, but on the next slide, this means nothing until you see pictures. That's how my brain works. So this would be an ice pack here, an extensive mass of floating ice. This would be an ice pack. This is an ice shelf, a massive portion of continental ice that projects out over the sea. And we saw in that video how Greenland is melting, right? You saw the calving from these ice shelves happening really, really quickly. Wasn't that a powerful video? Greenland will melt in our lifetime. And it's interesting because Greenland has enough water, frozen water, to supply Los Angeles with water for I don't know how many years they said. Can you imagine if we just saved that water, or we saved a little bit of ice and sent it over here? This is an ice floe, a large flat-ish piece of ice. I think this is like the iconic climate change picture, is like the poor little polar bear with no ice left. But actually, I don't want to be like, I don't want to take it lightly, because recently polar bears have been suffering. So they use that ice and all that time after they come out of hibernation, they use the ice that is left to kind of hunt and look for seals, and they need like 5,000 calories a day. So their hunt for that seal is very important. Now when they're coming out of hibernation, that ice is not lasting as long as it used to. So they're not able to hunt for seals like before. So now they're finding a lot of polar bears are going closer to where homes are. So they're digging in trash, looking for food. They're starting to eat things like dolphins, which scientists have never seen them eat dolphins before. And also you see a lot of polar bears dying of starvation because the ice is retreating so quickly. So during that spring when they come out of hibernation, there's still supposed to be ice and it's supposed to slowly melt, but now it's just melting so quickly. They don't have enough food and they don't have enough chances to hunt for that food. So I don't want to say like, oh, this, I wasn't trying to I was trying to be funny, but it's actually something that is happening. It's really sad. And our last one is this iceberg, right? A chunk of floating ice that breaks off from an ice shelf or glacier. And we know that these are very dangerous. This is what sank the Titanic, right? Only about 14% is exposed when it's an iceberg. Glacial ice covers about 10% of Earth's surface. So anywhere you see this light blue color, this is where we have our world's glaciers left here. Yeah, there's glaciers in Africa, in the high mountains of Africa. So only about 10%, and that's decreasing very quickly, like Glacier Park in Montana, I want to say. Yeah, Montana is disappearing. I don't know if there's any glaciers left, maybe one. So go visit a glacier. That's going to be like a sign of the times. Hopefully not. Hopefully we won't say, oh, remember where there used to be glaciers? That's actually scary stuff. Recently, formally stable ice shelves have broken apart. Look at the North Pole. It used to be that it was all unnavigable, but currently there are routes opening like from Russia into Canada, and Russia is actually setting up here and they are claiming these new routes, whatever. I never know if it's route or route, whatever. You guys know what I mean, right? I like to say route. So yeah, Russia is kind of like, yay, climate change. It's good because we're going to get warmer. And I'm being kind of sarcastic there, but they actually, they're doing a lot of offshore drilling. So that's also not helping the problem. And so, we're quickly losing a lot of the Earth's ice. Permafrost. Permafrost is another issue. A lot of our permafrost is melting, and that is a sign of the times in itself, but there's another problem that comes along with it. So permafrost is permanently frozen subsoil. You only find this really in these high latitudes. Soil contains moisture, and if it's cold enough, that moisture stays frozen, and it's been frozen for years and years and years. But now, because our temperatures are getting higher or warmer, a lot of the places where permafrost has been frozen forever, not forever, but you know what I mean, is now melting. And within that permafrost, you have these little trapped bubbles of methane, because within that permafrost, in the lake beds or close to the soil, you have decomposing organic material. So you have a lot of these decomposers or bacteria that are eating this, and they release methane. But instead of that methane being released into the air, it gets trapped within that frozen subsoil, okay? So you have bubbles of methane within permafrost. Now this permafrost is melting. So what does that mean? These methane bubbles are being released into the atmosphere. Remember, methane is 32 times more potent as a greenhouse gas than carbon dioxide. So like one carbon dioxide molecule, one methane molecule is 32 carbon dioxide molecules. So not only is permafrost melting because our climate is getting warmer, but as our climate gets warmer, more methane is released, which increases greenhouse gases, which increases more warming, which is going to increase more methane and CO2 to release from more permafrost. And it's just like this cycle. So this is another positive feedback effect. Things don't just, we're like at the tipping point, right? The tipping point really is like, it's bad, but then all these other like positive feedback effects are going to start revealing themselves, and it's just going to get worse, right? It's like this runaway effect, okay? Scary, right? I know. So here is our continuous permafrost in the very dark purple, and those lighter colors are sporadic. So in these lower latitudes, this is where we're seeing a lot of permafrost melt. And I'll have a link on the video. Because it's methane, you can literally poke a hole in the ice and light it on fire, because this is highly flammable gas. It's a very potent greenhouse gas. Organic matter decomposed by microorganisms, CO2 and methane, can be released when permafrost melts. This increases greenhouse gas concentration. It can also lead to damages to buildings, because you have, instead of that subsoil frozen, it's like a good foundation, right? It starts to melt and it causes like this liquefaction, and so buildings start to become affected by the melting of permafrost too. Oh, okay. Water use and resource problems. Water is a very important natural resource. We rely on it obviously for drinking, but also for our agriculture. And so some agriculture is very water intensive and some is not. So things like almonds, pomegranates, pistachios, cows, beef has a large water footprint. So it takes a lot of water to grow a cow. Think about how much grass and corn that cow needs to eat. That cow's supposed to eat grass, but now it's eating corn because there's not enough grass space, right? There's not enough space to grow grass. So think of all the corn that cow is eating, how much water it takes to grow that corn and to feed that cow. And then once that burger gets to your plate, it's a lot of gallons of water. So not only is beef incredibly not dangerous, how do I say this? The greenhouse gases and the fossil fuels associated with beef and the water footprint is a huge impact on our planet. Now, if only the United States ate beef, okay, that's still really bad, but all right. But now we have these other countries which also want to live our lifestyle, right? So Brazil is now a huge producer of beef, right? And so all these other countries want that American lifestyle. And when you think of America, what do you think of? Steaks and burgers and barbecue, right? So that's one reason I stopped eating beef. I think it's been 9 years now, and I don't miss it at all. You know, it wasn't like this huge sacrifice, but I said that, you know, I don't really need to eat it anymore. Although I do eat cheese, and I love cheese so much. I don't think I could ever be a vegetarian. Although I should be. I have a lot of students that become vegetarian because of my class, and I just feel really guilty. But every once in a while, no, I don't eat beef, but every once in a while I do kind of want a bite of my husband's burger. Um, And then when I do bite it, like it's so irony. It's like I could taste like the blood. Like I could taste it here, and I just like do the chew and spit. I think I'm talking too much about that stuff right now. All right, surface waters. Let's look at lakes, ponds, rivers, streams. These are all just types of surface waters. A lake is just defined as a body of water surrounded by land. There's no minimum or maximum size attached to it. A pond is just a very small lake. Lake Baikal is the world's largest freshwater lake by volume. So this is found in Siberia, Russia, right? Beautiful lake that actually freezes. And also, I think it's like this hidden secret people don't know much about Lake Baikal. It has the world's only freshwater seal, and this seal is called the Nerpa. It is a freshwater seal. All of our seals are saltwater seals. Pretty cute, right? Saline lakes, more than 40% of the lake water on the planet is salty. For instance, the Great Salt Lake in Utah, and I have a few videos attached to that. Formation of lakes, two things are necessary: as a natural basin with a restricted outlet and enough water to come in and keep that basin partially full. And this picture here is Convict Lake. The reason I put it is because the actual book, the textbook, has a picture of Convict Lake when they're mentioning surface waters or lakes. So I thought it was cool that I took that picture and I posted it. It's actually very beautiful. It's a glacier lake. It's close to Mammoth and Juneau Lake. I took a trip out there. I think most of you guys do this trip with Crystal Lovatier when you're taking the lab at Cerritos College. Absolutely beautiful. California has so much beauty to offer, guys. If you guys have time, take the 395, take it all the way to Bishop. And those white mountains, those Inyo Mountains, are absolutely beautiful, the Eastern Sierras. So much to see there. Mammoth Lakes, Juneau Lake, absolutely gorgeous. Wetlands. This is another type of surface water. They're broadly defined as land areas that are saturated with water, and they are very necessary. I don't know if I showed you guys. Yeah, we watched the video for Louisiana, right? Those coastal wetlands that are going to disappear because of the offshore drilling and because of rising sea levels. So those wetlands are extremely important. There's a little difference between swamps and marshes. A swamp has a plant growth that is predominantly trees, and then a marsh is vegetated by grasses and rushes. So it's like they're wetlands, right? But a swamp is more trees. A marsh would be grasses and rushes. There's a lot of marshes here in the LA basin. It used to be full of marshes and wetlands, but they were covered over when we were kind of populating the place. And in the past it used to be, okay, well, these wetlands just bring in mosquitoes, so let's just get rid of them, cover them over, build stuff over them. So there's a few left, and it used to be full of these wetlands, but there's not as many as there were in the past. Rivers and streams. A stream is just smaller than a river. Geographers, however, call any flowing water a stream, no matter what the size. And I think that's it for today, guys. I went through it really quickly. Look for your videos that go along with this lecture. And that's it. Go Dodgers. I'll see you guys later.